All right, so please be seated. We'll be starting shortly. Okay, good afternoon. Hope you had a good break and you had enough coffee, because these early afternoon hours can be dangerous, but we are chemists, we know how to handle that. And let's start with the two sessions we have for the early afternoon. And the first speaker alphabetically of this afternoon session is Jarad Mason. So Jarad, it's all yours, same rules. I will give you 5 minutes after 40 minutes. Please.
Okay, great. Thank you very much. I'm really thrilled to be here and have an opportunity to tell you a little about a research idea that I had over really the last couple of years. This is my first scientific trip in nearly 2 years, and so it's really a great pleasure to be here for such an exciting event. And so the idea I'm going to talk to you about today, or the dream I'm going to describe to you today, really started actually right after our lab shut down almost 2 Marches ago. And we had some extra time to sit around and think and try to come up with ideas for things that we wanted to work on. And so what I'm going to tell you about today involves a kind of unusual class of materials known as porous liquids that combine both intrinsic permanent porosity with fluidity. And I'm going to tell you a little bit about some ideas my group has for how to use these materials to address a really important problem related to delivering gases in a biomedical setting. Hopefully this is working. And so I want to start by just describing some general motivation for this dream proposal. And in particular, every day we breathe on average around 10,000 liters of air. And that's to get 21% of that air that we're breathing in is oxygen. And that oxygen is absolutely essential for keeping us alive. And the reason that oxygen is so essential is because of the critical role it plays in synthesizing adenosine triphosphate, or ATP, from adenosine diphosphate, or ADP, and inorganic phosphate, through this oxidative phosphorylation process. And so the synthesis of ADP is critical because this reaction, this conversion from ADP to ATP is energetically uphill. And the energy that's stored in ATP is used to drive many cellular processes. The synthesis of ATP from ADP is powered by an electrochemical gradient. And this electrochemical gradient across the inner mitochondrial membrane is created through the electron transport chain, where electrons are effectively transferred from glucose to oxygen as the final electron acceptor. This electron transport chain and ATP synthase is present in every single cell and every organ in our body. And so the oxygen that drives this reaction is absolutely critical. Cells, though, exist in an aqueous environment, and getting oxygen to a cell in an aqueous environment is a really significant challenge. And that's a significant challenge because of the fact that Water is a polar, strongly hydrogen bonded and associated solvent that has very little space to accommodate gas molecules. And water has very, very low gas solubilities, so about an order of magnitude below that of most common organic solvents. And so the solubility of oxygen under physiological conditions is on the order of about 0.2 millimolar. And so one way to think about this is that you have a single oxygen molecule in a volume of about 800 cubic nanometers. So oxygen molecules are spaced very far apart in water and are present in an extremely low density. And this density of oxygen molecules in water is not enough to sustain human life. And so that's why some of the earliest oxygen consuming life forms or organisms were very limited in terms of their size because they had to rely on the passive diffusion of molecular oxygen from the ocean into the organism. And the rate at which that can occur is very low because of the intrinsically limited solubility of oxygen in water. And so over the order of billions of years, hemoglobin and red blood cells and the circulatory system evolved to overcome some of these oxygen transport limitations. And the evolution of the cardiovascular system, which first appeared in animals about 600 million years ago, allowed the animals to evolve with a larger size, higher metabolic rates, and much greater sophistication. And so in blood contains red blood cells suspended in plasma. Plasma is mostly water and contains a selection of proteins as well as mineral ions and glucose and hormones and things like this, as well as some white blood cells for immune response and platelets for clotting during hemorrhage or during bleeding. Red blood cells themselves make up about 45% of blood by volume. And within our bodies, we have on the order of about 20 to 30 trillion red blood cells. So actually 84% of the cells in your body are red blood cells. And red blood cells, unlike most other cells in the body, do not have a nucleus, and they lack most of the organelles that are found in other cells. Their sole function really is to pack as much oxygen into as small a volume as possible so as to provide enough oxygen to support life. These red blood cells are bioconcave discs about 8 microns in diameter, about 2 microns or so thick. And so within each one of these red blood cells is a whole bunch of hemoglobin. So these are really just vesicles for hemoglobin, where as much hemoglobin as possible is packed together in a really tight environment. Within each red blood cell, there's on the order of about 270 million hemoglobin proteins. We have on the order of about 750 grams of hemoglobin in our body. And so hemoglobin is a metalloprotein. It contains 4 globular subunits. Each of these subunits, as many of you are probably well familiar with, have a porphyrin molecule or a heme unit that contains an iron 2 center, which can react through an electron transfer reaction to form an iron 3 superoxide and bind oxygen. Hemoglobin is about 6 nanometers in diameter. There's 4 hemes within each hemoglobin protein, so we're packing 4 oxygen molecules now into a box of roughly 6 by 6 nanometers rather than 20 by 20 nanometers as exists in water. And so this is dramatically increasing the density of oxygen molecules that are present, and there's about a 70-fold increase in oxygen density in blood compared to pure water, and that's what provides enough oxygen to allow us to really be alive. Oxygen from red blood cells is transferred to tissue and cells that need the oxygen for respiration through passive diffusion mechanism or through active diffusion, where molecular oxygen is released from hemoglobin and red blood cells into the plasma, where again you're limited by the solubility of oxygen in water, and then transfers diffuses according to Fick's law out to surrounding tissue that are in need of oxygen. So the rate of diffusion of oxygen from red blood cells to surrounding tissue is going to be a function of the distance that the oxygen has to travel, as well as the concentration or partial pressure gradient in oxygen, or the diffusion constant, the partial pressure gradient in oxygen, and the distance inversely proportional to the distance that oxygen has to travel. So the partial pressure gradient is typically fixed. Arterial blood has a partial pressure of oxygen on the order of about 130 millibar. Most tissues are at about 50 millibar. So this is the partial pressure gradient that provides the driving force for oxygen to be released from hemoglobin and to diffuse into surrounding tissue. Because you're limited by the low oxygen solubility of water, there's a driving force to have these oxygen reservoirs, or red blood cells, as close as possible to tissue that needs it. So typical distances are on the order of 10 to 30 microns between blood vessels and surrounding tissue that need oxygen. It's very rare that oxygen has to diffuse more than 100 microns in the body because of the really low solubility of oxygen. So disruptions to the delivery of oxygen to tissue are obviously extremely poorly tolerated and can be catastrophic. And so I'll walk through a few examples of situations in which O2 delivery is impaired, either by decreasing the partial pressure of oxygen that's present in blood, or by the flow of blood being stopped by something like a heart attack. And talk a little bit about some of the impacts that has. So one example of this is acute respiratory distress syndrome. So an acute respiratory distress syndrome is a situation in which the lungs become injured and are unable to take in enough oxygen and expel enough CO2 to keep up with metabolic demands. An acute respiratory distress syndrome, often mechanical ventilation or intubation plus mechanical ventilation is used to get air, oxygen into the lungs. But with injured lungs, this can be really difficult to do. And so there's about a 30 to 50% mortality rate from patients that suffer from this. And this has been a huge problem during the COVID pandemic as well. And it's really challenging to get oxygen into somebody when their lungs are not functioning properly. One kind of last ditch kind of way that can be tried to get oxygen into the bloodstream when the lungs aren't working properly is a technique that's known as extracorporeal membrane oxygenation, or ECMO. This is basically like a dialysis machine where your blood is connected to an external circuit, goes through an oxygenator, and is returned to your body at a higher PO2. And so this is a good way to get oxygen into the body, but it's fraught with a lot of complications. So flowing blood through this kind of external circuit often leads to thrombosis or blood clots that can lead to blockages of blood flow. And so patients are often given an anticoagulation agent like heparin to prevent blood clots from forming, but that can inversely lead to severe hemorrhages. And so about 5% of patients that are connected to this kind of instrument suffer from a fatal brain hemorrhage. And so this is a really challenging technique to implement. It's also very expensive and only available in very specialized settings inside a hospital. And it's not at all suitable to addressing emergencies that occur outside of a hospital setting. Things like a heart attack or cardiac arrest, where blood flow completely stops and circulation completely stops. So heart attacks can result from a blockage in a blood vessel that stop blood flow, or airway obstruction, and that lead to a stop of circulation. And so heart attacks are typically treated by performing CPR, which restores about 25% of your blood flow, forcing oxygen into the lungs. That requires, though, a functioning airway unit and doesn't do much if you have an obstructed airway. And so having this impaired oxygen delivery almost instantaneously causes tissue damage, and on the order of minutes can be fatal and lead to irreversible neurological damage as the brain tissue becomes hypoxic or deprived of oxygen. And so outside of a hospital setting, there's roughly 4.2 million cardiac arrests that occur worldwide, and the 1-month survival rate from having a heart attack outside of a hospital is on the order of about 11%. So really low, and there's just really not great treatment options for something that is relatively simple of just trying to get oxygen into your body to prevent tissues from becoming severely hypoxic. Right? We're surrounded by oxygen, but getting it in is really not a trivial task. And so one thing that people are very interested in for addressing this is having some way of rapidly, through a bolus or single dose injection, of getting oxygen into the bloodstream as kind of a bridge therapy to more advanced life support measures. So what if you had something in a syringe that you could inject into a blood vessel to rapidly increase oxygen tension within the blood and buy yourself time to prevent this kind of severe tissue damage from occurring. So it's not just emergency situations or things that are acute, like heart attacks, where treating hypoxia is an issue. This is also a major problem in cancer. So tumors are incredibly hypoxic environments. Right? So tumors consist of rapidly proliferating cells and typically proliferate to form very kind of disorganized and leaky blood vessels that typically do not have very great blood flow and do not do a good job of delivering oxygen to cancerous cells. And so across a wide range of different types of cancer, the metastatic potential or severity of cancer is almost directly correlated to the degree of hypoxia within the tumor. So the more hypoxic your tumor is, the more likely it is to select for very aggressive tumor cells, and the more likely it is to metastasize aggressively. The degree of hypoxia is also inversely correlated to a variety of different treatment options or therapies for addressing cancer. And I'll show that in a second, but here is just an example of the partial pressure of oxygen that's found, in average partial pressure of oxygen shown here, that's found across a variety of different types of cancer. And this can be compared to partial pressure of about 40 millimeters mercury for normal tissue, so severely hypoxic environments. So as an example of where this is a problem, one of the most common ways to treat tumors is through radiation therapy. So radiation therapy kills cancerous cells by radiation ionizing DNA and leading to irreversible breaks in double-stranded DNA that then in turn induce cell death. So you radiate a tumor, you form a free radical on DNA. If there is not oxygen present, free thiol compounds or molecules in the surrounding environment can reverse this damage, it can reduce the DNA back to its original native form. If oxygen is present, then this damage can effectively be fixed into the DNA by forming a reactive oxygen species covalently bound to the DNA, and this leads to a double-strand break in the DNA, as I mentioned, in cell death. And so the efficiency with which radiation destroys cancer cells is directly related to the partial pressure of oxygen that's present within the tumor. The lower the partial pressure of oxygen, the more radiation that's going to be required to induce a given amount of cell death or get a lower amount of cells that are surviving. And the more radiation you have to use, the more potential there is for damaging normal tissue, healthy tissue around the cancerous area. This is also true for photodynamic therapy, where a photosensitizer is used to generate a reactive oxygen species to similarly induce cell death. The efficacy of photodynamic therapy is directly related to the partial pressure of oxygen that's present in the tumor. And so since the 1960s, people have been trying to develop strategies for reversing hypoxia in tumors and getting oxygen into tumors before employing radiation treatment or photodynamic therapy. But that's something that's really challenging to do. And there's been very limited success in clinically translating different kind of approaches to doing that and putting them in practice. There's challenges with administration, and there's also challenges with toxicity to normal tissue rather than just the cancerous tissue. So all of these different kind of situations I've described are kind of unified in terms of having a fundamental challenge of effectively being able to deliver oxygen in an aqueous environment when our fundamental biological mechanisms for doing so go awry. And so this is the challenge that my dream proposal is really trying to address, trying to come up with strategies for overcoming the low solubility of oxygen in water as a way of treating hypoxia across a variety of different conditions. And so the most obvious way to think about getting oxygen into the bloodstream when it's needed is just take a syringe of oxygen gas and inject it in the bloodstream, right? And that's really not a viable option. The amount of oxygen that we need to stay alive is on the order of about 230 mils per minute. The amount of oxygen, though, that can be safely injected is less than about 19 milliliters of oxygen per minute. And that's because you very quickly have air bubbles or oxygen bubbles that form in your bloodstream or that do not collapse and can lead to fatal embolisms or blockage of blood flow in different areas in the body. And so direct gas injection is just not a viable strategy for getting oxygen into the body. It's actually a really good way to kill people. And this is actually a Belgian serial killer that was arrested in 2014, killed between 10 and 20 people by directly injecting air into their IVs. And it doesn't take much, just half a mil of air in your brain blood flow will lead to death, and 2 mils in the coronary artery of air can lead to death as well. So you can't directly inject air. So there's been a lot of interest in trying to find alternative ways of delivering oxygen. And so a lot of this work really started in the 1960s when people were interested in finding alternatives to using donated human blood for treating trauma. And so about 30 to 40% of trauma is fatal because of catastrophic blood loss. And most of that trauma results from violence and car accidents, really. And so there was a lot of interest in trying to find ways of being able to treat severe blood loss without having to use donated human blood in the 1960s. And this really accelerated in the 1980s with the HIV epidemic around the world. Sorry, I'm not sure exactly what's going on here. So I'll try to continue talking while this is going on. So the issues with donated human blood include things like mismatch in supply. So where the donated blood is available and the number of donors that are available and is often mismatched to the need for blood. It's not available usually in far forward locations like catastrophic events that occur and things like that. One has to be concerned about contamination of blood with viruses. This is no longer really a problem in the developed world, but can be a significant problem still in the developing world. There's issues with having it available where and when you need it, and blood, of course, has to be matched to the blood type of the individual that's receiving it. And so since the 1960s, there's been a lot of work done in trying to develop artificial blood substitutes. There's really a couple of different approaches that people have taken to doing this. One is to try to directly mimic nature and to bind oxygen in some sort of carrier chemically. Usually this takes the form of cell-free hemoglobin, so hemoglobin that's outside of a red blood cell, or some type of inorganic heme mimic, so a molecule that's designed to reversibly bind oxygen through electron transfer and release it. Cell-free hemoglobin is really hard to get to work as an artificial blood substitute or even just any kind of oxygen carrier because hemoglobin itself outside of a red blood cell is extremely toxic. So it leads to large increases in blood pressure. It can cause strokes and heart attacks. It also accumulates in the kidney and causes significant kidney damage and can pretty rapidly lead to kidney failure. So hemoglobin, which keeps us alive, is actually quite toxic when it's outside of its native environment, inside a red blood cell. So there's been a lot of research done on trying to get cell-free hemoglobin to work as an oxygen carrier. There's never been anything that's been clinically approved or demonstrated to be viable. The alternative approach is not to bind oxygen chemically, but to have it physically dissolved or absorbed in some sort of solvent or medium. And so I'll talk a little bit about the approach that's been used most commonly there, and that is to dissolve oxygen in what's known as a perfluorocarbon liquid and to form an emulsion of that perfluorocarbon liquid in water. And so the reason perfluorocarbons are of interest for oxygen delivery applications is because they have much higher solubilities than many organic solvents and significantly higher, about an order of magnitude higher than that of water. And so if you look at the oxygen solubility in water compared to just a normal hydrocarbon like N-heptane to the perfluorinated analog has nearly double the oxygen solubility because perfluorocarbon molecules are very rigid, have weak interactions. They actually have quite a bit of free volume in the liquid state, and it's much easier to absorb and accommodate oxygen molecules in those liquids. And so perfluorocarbons actually back in the 1960s were used for a very famous experiment where a mouse was submerged in a perfluorocarbon liquid that was oxygenated with pure oxygen and could actually breathe in and out the liquid for, in this case, around 4 hours, stayed alive, and then was completely fine after getting out of the liquid. And so this works because perfluorocarbon liquids contain so much oxygen that they contain enough oxygen, unlike water, to actually support life. And so there was a lot of interest in taking these perfluorocarbon liquids and not using them for liquid breathing, but actually using them as artificial oxygen carriers for treating many of the types of things that I previously discussed. And so you can take perfluorocarbon liquids. They're not miscible with water. They really don't like water. But you can form emulsions in water with things like phospholipids and block copolymers to form droplets of perfluorocarbons surrounded by some type of surfactant that can be then dispersed in water and can be considered as an oxygen carrier. In this particular case, this is often referred to as an artificial blood substitute, but the only function of blood that it is substituting for is the transport of respiratory gases. So taking oxygen where it's needed and taking CO2 away. None of the kind of signaling or immunological functions associated with blood. And so there has been a lot of research and development in using perfluorocarbon emulsions as oxygen carriers. In the late 1980s, there was a perfluorocarbon emulsion that was briefly approved by the FDA for use in coronary angioplasty surgery, so widening of coronary arteries that are blocked. But it was withdrawn in the mid-1990s because of issues with stability and also dose-limiting toxicity. So where perfluorocarbon molecules were accumulating in organs in the body and causing a lot of different issues. These fluorocarbon emulsions also don't have that high of oxygen capacity, so much higher than water, but it's still really hard to get up to similar oxygen density as what is present in blood. And these are just two examples of different fluorocarbon emulsions. And so as I mentioned, the stability and shelf life of these perfluorocarbon emulsions is a major challenge. And so these droplets are very weakly associated perfluorocarbon molecules. And so they're prone to things like Oswald ripening, where particle sizes grow over time. And that can be problematic because once your particle sizes start growing to on the order of microns, they can cause blockages of blood vessels and embolisms. And that can be a significant issue. So the shelf life of these is really not great. And also because the oxygen capacities aren't so high, you need a lot of them to have an impact, and that leads to toxicity issues. And so my group got really interested in thinking about alternative approaches for being able to deliver oxygen, and that's really the heart of the dream proposal. And so what does one look for in thinking about an ideal carrier for delivering oxygen in an in vivo or even in vitro kind of setting? Well, you want a high oxygen capacity, right? You want to be able to cram as many oxygen molecules into as small a volume as possible. For one, that means you're going to have to use less of a foreign substance to get a given amount of oxygen into the body. And so that has a lot of advantages from a toxicity perspective. You want your oxygen carrier to bind oxygen reversibly, right? It not only needs to store a large amount of oxygen, it needs to be able to release that oxygen, and needs to be able to release that oxygen where and when it's actually needed. You want to have relatively fast kinetics. The desired kinetics depend a little bit on the application, but for particular applications where you have severe hypoxia and you want to just quickly get as much oxygen as possible into an area, rapid kinetics are quite important. And you, of course, want to have minimal toxicity. And so my group became particularly interested in thinking about using porous materials and microporous materials for oxygen delivery in aqueous environments. That's something that's really challenging because most porous materials will just fill their pores with water under normal in an aqueous environment and lose the high gas capacities that they typically have. And so I'm just going to introduce a little bit about microporous materials, why they have high gas capacities and why we were interested in them for this application, and how I'm thinking about actually being able to use them in water. And so microporous materials are materials that have pore sizes on the order of about 2 nanometers or less. And these materials have extremely high internal surface areas. You can just do a simple thought experiment. If you imagine a cube of a solid substance, about 1 centimeter on edge, and you start drilling holes into that cube, you will quickly start increasing the surface area of your material as you go from 1 millimeter pores to 1 micron, 100 nanometer, down to the microporous regime of 1 nanometer or 5 angstroms, the amount of exposed surface area within the same volume substantially increases. So for 5 angstrom pores in this particular cube, you have a surface area on the order of about 5,000 square meters. And so for some microporous materials that have some of the highest internal surface areas, the surface areas are actually, for a relatively small amount of material on the order of about 2 milliliters of a microporous material, the internal surface area is equivalent to that of, in this particular case, this is an American football field just south of Boston where the New England Patriots play. But in just that tiny volume of material, you have incredibly high surface areas. And so that's an incredible amount of space to interact with gas molecules. So the internal surfaces of these porous materials can absorb gas molecules, bring them closer into the pore surface, cause them to pack more densely, and that allows you to store a really significant amount of gas. And so we can return back to our kind of box showing how much space is required to contain a single oxygen molecule in different environments. Now we're up at under physiological conditions of about 1 bar and 37 degrees C. So in pure water, a single oxygen molecule is in a box about 11.5 nanometers on edge. In blood, that's reduced down to 5.7 nanometers because of hemoglobin chemically binding oxygen. This is still, though, less dense than what's actually present in just normal oxygen gas outside of a liquid environment at 1 bar and 37 degrees. But with a microporous material, we can actually compact oxygen and pack it even more densely together because of the phenomenon of adsorption on internal surfaces. And so most microporous materials can have a single oxygen molecule in a volume of about 1 to 2 nanometers, a cube of about 1 to 2 nanometers. On edge. And so this allows you to significantly increase the volumetric oxygen density that you can store in a material. So in a microporous material, you can far surpass the density of just the bulk gas phase. And so the particular types of microporous materials that my group has been interested in for this application are both metal organic frameworks and zeolites, a hybrid class of microporous materials, and an all-inorganic one. And I'll just briefly describe some aspects of these two different classes of porous materials. So metal organic frameworks are typically composed of single metal cations or small inorganic clusters, like this zinc 4-oxo cluster that's shown here, where these tetrahedron represent tetrahedral zinc atoms linked by a mu4-oxo in the center and surrounded by, in this particular case, 6 bridging acetate ligands. And so these inorganic units are bridged by bridging organic ligands to form 3-dimensional crystalline extended framework materials. So in this particular case, these acetate moieties have octahedral points of extension, so up, down, right, left, one going into the screen and one coming out of the screen at you. And so if you imagine replacing them with a bridging ligand like terephthalic acid, 1,4-benzene dicarboxylate, you can imagine linking these in 3 dimensions to form a 3-dimensional porous material. And so in this particular case, these have pore sizes on the order of about 1 nanometer and have incredibly high internal surface areas like we talked about previously. Zeolites are inorganic materials, typically silicates or aluminosilicates that are composed of corner-sharing SiO4 or aluminum O4 tetrahedra. So by corner sharing, I just mean that single oxygen atom is bridging between these two different silicon centers. And these can link together in a variety of different ways to form extended framework materials that can have similarly high surface areas. So both zeolites and metal organic frameworks are very tunable classes of materials that can adopt a wide range of different extended structures with a variety of different pore sizes, shapes, and internal surface chemistries. And they can have incredibly high oxygen adsorption capacities. So this is just an example of a couple different metal organic frameworks and some zeolites and their oxygen densities in comparison to bulk gas phase, perfluorocarbon, and water. And so these densities are extremely high of gas molecules, and they account for the fact, and that's even including the amount of space that's taken up by the actual solid component of the framework. Because of adsorption, they're really cramming gas molecules together. It's very tightly. And so what I'm interested in is thinking about, can we leverage these high reversible gas capacities to actually overcome a lot of the challenges that I described previously with regards to delivering oxygen in an aqueous environment. And so there's precedent for using microporous materials to think about gas delivery within a liquid environment. And so there was work done relatively recently by Stuart James at the University of Belfast and Andy Cooper at University of Liverpool, where they looked at organic cage molecules. And these kind of look like you took a bunch of crown ethers and kind of stuck them together. And they dispersed these in a really bulky crown ether-based solvent, where the solvent molecules are too big to diffuse inside these organic cages. And so what that led to was a liquid that had permanent porosity. The interior portions of these cages were empty, but accessible to gas molecules. And so this led to significant increases in the amount of gas that could be stored in the liquid because of these voids that could accommodate gas molecules. And this has been expanded to other types of microporous materials, including metal organic frameworks and some zeolites, by dispersing nanocrystals of these materials in really bulky, viscous organic solvents that are too large to diffuse inside the microporous networks of these materials. This doesn't work, though, for water. You can't rely on sterics to prevent water molecules from going inside any microporous material, because water is going to be smaller than any gas molecule and, of course, than oxygen that we would want to host inside. And so in water, pores of most microporous nanocrystals will fill with water, they'll lose their high internal surface areas and lose their gas capacities. But one can rely on a different strategy, so a thermodynamic strategy, to preventing micropores from filling with water in an aqueous environment. And so this is something that happens commonly in proteins, where hydrophobic side chains provide a thermodynamic penalty for water molecules to fill cavities that should be large enough to accommodate water molecules, and this leads to permanently dry cavities inside a protein. Similarly, for microporous materials, if you have a very hydrophobic microporous solid powder, put it in contact with water, it will require mechanical pressure to force water to intrude into the pores of that material, and the pores will be dry in their native state. And so inspired by this, we are dreaming of a thermodynamic strategy for creating permanent microporosity in water that can lead to really high local concentrations of oxygen gas. And so you can think about taking materials that have very hydrophobic internal pores such that it's thermodynamically unfavorable for water molecules to go inside. This can be both enthalpic and entropic. So entropic, because confined water molecules have less mobility and degrees of freedom inside a porous material than in the bulk phase, and enthalpic, because surface water interactions inside the porous material are much weaker than water-water interactions in the bulk liquid phase. So it's thermodynamically unfavorable for liquid water to fill these micropores, but it is thermodynamically favorable for gas molecules to go inside and to be absorbed. And so this was our idea. How do you think about doing this? Most hydrophobic materials do not want to be dispersed in water. And so the way we think about doing this is creating porous materials that are really hydrophobic in their internal pore surfaces, but have a hydrophilic external surface such that they can form uniform dispersions in water, but for which it's thermodynamically unfavorable for gas molecules to go inside. And so I'll just quickly walk through an example to show you some very recent results that show that this general framework for thinking about how to create porosity and high gas capacities in an aqueous environment does in fact work. And so we can take a really hydrophobic zeolite. So zeolites with high silica contents are quite hydrophobic. Their internal surfaces are very nonpolar. But their external surfaces are quite hydrophilic because they're terminated in surface silanol groups. And so we can synthesize a hydrophobic zeolite with very uniform particle sizes. These form really nice dispersions in water. They're translucent, look really just like pure water. And so this vial is filled with a dispersion of 10 volume% of these zeolite nanocrystals that are about 60 nanometers in size. And this looks just like water, but we can show through density measurements and direct gas absorption measurements that the pores of these zeolite nanocrystals are completely dry. So these solutions can have on the order of between 3 and 20% empty space. We're really excited about this because this allows us to have oxygen densities in an aqueous environment that are extremely high. So for just a 3.6 volume % dispersion, we could already match the oxygen density that's present in blood. Right? And this is with very little amount of foreign material, so mostly water. We can already get oxygen densities that are comparable to that of blood and that far exceed that of fluorocarbon emulsions at much, much higher concentrations. If we go to higher concentrations, we can get to even higher oxygen density. So at an oxygen density, at a nanocrystal density of just 12.5 volume %, we can match the density of bulk oxygen gas. And that's not something that's ever been exceeded by any kind of synthetic artificial oxygen carrier. If we go to even higher densities or concentrations, we can far surpass the bulk oxygen density. So this is something we're really excited about because there's really no other way of localizing such a large amount of gas in such a small amount of space. And we think this has tremendous potential for addressing a lot of the challenges related to hypoxic conditions that I talked about previously. And so our dream is to really be able to leverage these kinds of design principles in order to address a lot of these biomedical challenges. And we've shown that we can take these solutions and we can deliver oxygen from our solutions to deoxygenated or hypoxic red blood cells in some very preliminary experiments demonstrating kind of just the basic potential of this. We're not limited at all to working with zeolites. We can work with metal organic frameworks and a variety of other microporous materials, even ones that don't have intrinsically hydrophilic surfaces. So we can propose ways of making hydrophobic surfaces hydrophilic, external surfaces, so that we can do take a very similar type of approach to increasing porosity or to having porosity in an aqueous environment. So we can think about covalently functionalizing hydrophobic microporous nanocrystals with amphiphilic or hydrophilic surface ligands, as well as non-covalent functionalization with macromolecules like polymers or even proteins to allow us to form similar types of really uniform and stable dispersions that have high oxygen capacities. So there's a tremendous amount of tunability on these systems because we can tune the identity of the nanocrystal, the size and shape of the pores, the chemistry of the internal surfaces of the material, as well as the chemistry of the external surface to impact things like stability in different types of physiological media, toxicity, kinetics of gas release, interactions with proteins, protein corona formation, degradation, the in vivo fate of the nanocrystal, and all kinds of things like that. And so some of just to kind of summarize, advantages of these systems are the incredibly high gas concentrations that we have and the tunability of these types of materials that allow us to really tailor properties for different types of applications. And so I'll just end by saying that in addition to some of the medical interest in addressing medical applications related to hypoxia that I described at the beginning, we think this platform also has a lot of potential not just for in vivo applications, but in vitro as well. So delivering oxygen in an in vitro setting is even more challenging to some degree than in an in vivo setting because you don't have vasculature. So getting oxygen in when you're trying to preserve organs or grow tissue, for example, is a really big challenge where we think this kind of general approach to creating permanent microporosity in water and having high gas capacities can be really impactful. Outside of the medical side, there's energy-related applications where we think this also has a lot of potential. So high-pressure gas separation, such as CO2 removal from different acid gas streams, cannot be done using water as a solvent. They're often done using environmentally harmful organic solvents because they have much higher gas capacities. And we think this approach provides a way of moving these to much more environmentally friendly solvents. Also in the context of electrocatalysis, any kind of situation where you need to get a high flux of gas through an aqueous environment, we think this has potential. So something like CO2 reduction or nitrogen reduction, where the rate of your catalytic reaction is often limited by the concentration of gas at the electrode surface. We think this has a lot of potential for doing some interesting things there. So let me close by just acknowledging and thanking my research group and the people in the group that contributed to some of these ideas. I'm fortunate to work with some really talented students and postdocs, and thank the organizing committee for the invitation to be here. And I'm super excited to be here, and it's been a really fun visit, and looking forward to the rest of the day and interacting with labs on campus as well. So thank you all for your attention.
Thank you very much, Jarad, for great talk, great timing, you have time for discussion. Petr Slavič.
So actually, if you were able to repeat the mouse experiment from 60s and with humans, you can also transform the field of scuba diving industry. Maybe with this, but my question is following. So what is actually the thermodynamical force which then will lead to the transport of the oxygen from the nanoporous materials to the red cells? Because it seems that it binds the oxygen much better than the red cell itself. So isn't the net result that in the end it would just stay in the microporous material?
Yeah, so that's an excellent question. And so it depends on exactly how what you mean by better, right? So it binds oxygen better in the sense that it packs a lot of oxygen molecules together more closely. And that's really a function of this high internal surface area. It actually does a really poor job of interacting from an energetic perspective with oxygen. So the binding energies of oxygen with the internal surfaces of these materials is on the order of, say, 10 to 15 kilojoules per mole, compared to probably more like 60 to 90 kilojoules per mole for covalent oxygen binding in hemoglobin. So it's actually a really weak physical interaction between oxygen and the porous surface that's more similar to like oxygen being dissolved in water or perfluorocarbon liquid. So that thermodynamic force for oxygen release is really just a partial pressure gradient. So it goes from a high PO2 environment to a low PO2 environment, and there's basically no activation energy barrier to that happening. So these are fully reversible with pressure.
So do you have some idea on the free energy change for the transport from the microporous material into the red cell, for example?
Yeah, so the free energy change is on the order, well, the free energy change is a little more challenging, but the enthalpy change is on the order of about 13 kilojoules per mole, which is very similar to like a perfluorocarbon liquid. So if you look at gas absorption into the solutions as you increase pressure and then decrease pressure, it's fully reversible with no hysteresis. So if you go from your oxygenated liquid to hypoxic tissue, oxygen will rapidly be released until you equilibrate the two partial pressures and eliminate that kind of chemical gradient or partial pressure gradient. And so that happens very quickly. So it's all driven just by pressure differentials.
Thank you for the interesting lecture. I have two questions, if I may.
Of course.
The first question, what would be the optimum geometry, the optimum size and shape of the zeolite particles for oxygen transport? And then I ask second later.
Yeah, that's a great question. I think it depends a lot on the application. So the in vivo fate of the nanoparticles is obviously extremely important, and that's a huge challenge for translating any kind of nanoparticle technology into the clinic. And so if you can do this with particles that are sub 13 nanometers, then that offers the possibility of the particles being cleared renally through the kidney and just excreted through urine, rather than accumulating in organs. And so I think that actually is probably the sweet spot for being able to do this, because you could get oxygen in really quickly and then you get your foreign material gone rather than stuck around in the body. Because if you put enough of anything in the body, it's going to be a problem. So I think that kind of size regime is really optimal for a lot of these kind of applications where you want to get oxygen into the bloodstream. 100 to 200 nanometers is typically what most people are thinking about for this kind of thing. If you get much bigger than that, then you run into issues of blocking blood vessels and that kind of thing.
And what about the shape? Would it
yeah, shape is
like the red blood cell?
Shape is a great question, and not something we've looked at closely yet. You probably don't want anything too anisotropic, because if you make fiber-like kind of things, that can cause issues. But in terms of like flat versus curved facets, it's very interesting, particularly once you start thinking about surface functionalization, and not something I have a good feel for. I think it probably depends on the specific application, but that's something we're definitely investigating or plan to investigate.
Thank you. And may I ask the second question? No, size and shape was one. Now, the second question would be, you touched upon it, the accumulation in the organs. Are there other long-term side effects which could...
Yeah, so I think accumulation of organs is probably the biggest. This platform is so tunable that it really depends on exactly what the composition of the nanocrystal you're going to use is. Is it a metal organic framework? Is it a zeolite? What's the metal? What's the organic ligand? And depending on that, I think there can be a variety of toxicity concerns. There's the potential for making particles that degrade to just form salt effectively over some time scale, and that offers ways of addressing things. But yeah, I think every different composition is going to have behave differently in an in vivo setting, and that's something that definitely needs to be understood. But that's the advantage, I think, of having this high tunability, is that there's really just infinite possibilities for thinking about how to do this.
So, very nice talk. Congratulations. I will continue in this question. I'm wondering, what's the toxicity? What is known about moths and zeolites and so on? How they are behaving within the organisms?
Yeah, great question. So there's a fair bit that's known for moths and a little bit that's known for zeolites. So most silica materials do have some cytotoxicity. There's been a lot of effort to develop silica nanoparticles as drug delivery vesicles, and so there's a lot that's known there. There are some advanced clinical trials of porous silica materials, not zeolites, but very similar, for drug delivery applications. I think in a lot of those cases, it really depends on the surface functionalization. So if you have a surface that's terminated in silanol groups, you're going to be in trouble because that's just going to rip apart cell membranes. But as soon as you passivate that external surface, then you can do a lot of things. And so I think, since water doesn't go into these materials, really the only thing that's going to be seen by the body is the external surface. And so it all comes down to external surface functionalization. So it's known if you take silica materials and you alkylate the surface, for example, you can dramatically reduce toxicity. And then for moths, there's just so many different moths because you can control the metal cation and the bridging organic ligand, that some moths have very limited cytotoxicity, at least in the applications for which they've been evaluated, and some are incredibly cytotoxic. So it really depends a lot.
And what about accumulation in some organs? Is it something known?
So it's not something that's been very well investigated. It depends a lot on particle size, and that's where I think the advantage of going to small particles really would be, because the thermodynamics of what we're trying to do and what happens in terms of preserving porosity and having high gas capacities doesn't change with size. And so if you can make sub 13 nanometer particles that could be cleared renally, then you don't really have to worry about organ retention. If they're higher, then they're going to get taken up by lungs, liver, spleen, and that could be a problem, as it is for many nanoparticles. So that's definitely something to keep in mind.
Yeah, thank you very much for the talk. Oxygen is, of course, a diuretical, right? And you were always talking kind of physical binding. Are there any oxygen-oxygen contacts which change the spin properties of oxygen? That would be the first. And the second is, can you displace oxygen by other gases in these, let's say, carbon dioxide, carbon monoxide? So how stable is the system in the presence of other gases?
Sure, yeah, both really interesting points. I'll answer the second one first, maybe. So in terms of other gases, so one advantage of these is that they do take up a large amount of CO2 as well. So they're functioning not just to deliver oxygen, but to remove CO2. And one can model the selectivity for gases. So CO2 will be taken up to a greater extent, but it's present at a lower partial pressure. So it doesn't actually interfere with oxygen capacity. CO will be taken up as well. And so these can potentially be thought about as CO scavengers to treat CO poisoning, which is maybe what you were kind of alluding to. In terms of displacing with the gas, though, that's not something we've looked at yet. So most gases at the kind of pressures you would find them in a physiological setting would not be absorbed enough to really outcompete oxygen. So they wouldn't really work to displace oxygen. You really have to flood the pores with something like a liquid at a really high density to be able to do that. Sorry, your first question.
Oxygen is a diuretic.
Oh yes, diuretical. So yeah, these
oxygen contacts.
Yes, yeah. So these are really weak interactions, and so oxygen is packed together tightly, but oxygen molecules don't see each other at these pressures really, and so oxygen is itself unchanged in these kinds of adsorbed settings. In certain moths, you can think about incorporating low coordinate metal centers that don't necessarily bind covalently, but kind of in a regime between non-covalent and covalent interaction, in which case you can see some really interesting changes in oxygen binding, and that's something that one can think about as well.
Okay, thank you.
Hi, thank you for the talk. So blood is a very complex environment filled with lots of proteins and carriers and enzymes and molecules. Is there a possibility that after you spend several years of beautifully designing your system, then you will inject it in the blood, and actually lots of components will block the hydrophilic groups or hydrophobic groups, or interfere with the release of oxygen back into the red blood cells? So did you actually try some experiments already in the blood, whether there is that danger?
Yeah, so that's a great question. And I think there's a lot of things that could certainly go awry in blood. We have done preliminary experiments where we look at showing, at least for packed red blood cells, and we've looked with plasma as well, that you do see the expected amount of oxygen that's released when you inject an oxygenated solution into deoxygenated blood. So I don't think there's going to be anything that goes on that inhibits oxygen release. Most of the systems we're working with are very stable, and so there's nothing in blood that would degrade the nanoparticle itself. There's certainly plenty of things, though, that can go awry inside blood, and something that has to be thought about. But we know that oxygen will be released to red blood cells in that type of environment. So I think there's definitely the possibility that one could spend a lot of time on this and not develop something that's viable as an artificial blood substitute, because that's very challenging and something that people have been working on for a long time. It's definitely a dream, but we can show for sure that the oxygen release does go according to plan.
Thank you very much.
Yeah.
Yes, the hemoglobin oxygen dissociation curve has a characteristic sigmoidal shape.
Yes.
Whereas most equilibrium absorption isotherms of oxygen on zeolites has a characteristic Langmuir type of shape.
Yeah.
Don't you see a problem there?
Yeah, so that's an excellent question. And so the answer to that is that the cooperativity of hemoglobin itself doesn't matter that much in terms of the actual amount of oxygen that's released when you're swinging between the partial pressure of, say, 100 millitorr and 40 millitorr. In that regime, it's actually relatively linear. But even if it was cooperative, what matters is how much oxygen do you store at that high partial pressure and how much oxygen that you just store at that low partial pressure. What the shape of the isotherm in between those two pressures is actually less relevant for a lot of these applications. But what can happen with most linear isotherms is that you just don't have as much difference between those two partial pressures. With these materials, though, because of their high internal surface areas, even though the isotherm is linear, you actually have a much larger change between those two partial pressures. So you can release more oxygen between those two pressures, and you don't have to rely on like allosteric effectors like hemoglobin does to facilitate the release. So it's very similar to how like a perfluorocarbon emulsion functions, where you have also a linear isotherm. So you're exactly right in that the behavior is different, but I don't think it presents any kind of intrinsic limitation for an actual application, because again, it's really just the difference between those two partial pressures that ultimately matters.
So maybe just for clarification for me, so is your strategy releasing the oxygen from the nanoparticle to the red blood cells or directly to the tissue?
More directly to the tissue, though if red blood cells are around, then these can work in synergy with red blood cells, so kind of like hopping points, and that's how people think about perfluorocarbon emulsions as well. So these are like local environments of high concentrations of oxygen that can facilitate diffusion. And so, if there's red blood cells around, then it'll release to red blood cells, and then the red blood cells will release to the deoxygenated tissue. It's kind of like an oxygen buffer, in that you're just generally increasing the concentration of oxygen that's present. In an in vitro application, of course, you don't have red blood cells to worry about, and so there it's coming directly from your particles to the cells that are need to metabolize it.
Okay, well, thank you very much again. And last but not least, this is like what you always say before the last lecture, right? Giulio, Ragazzon, it's all yours. Same rules, same conditions apply.
Can you hear me? Yeah, perfectly, very strongly. Okay, let's put this here. Okay, so good afternoon, everybody. And first of all, thank you very much to the organizers for letting me be here today, because this was not granted at all. And when I was preparing my presentation and preparing to arrive here in Prague, I tried to learn a few things about dreams.
And so I asked myself, how do people dream? What do they dream? And yeah, how do they dream? So one of the answers that to my surprise, was that many people dream in pastel colors. And then another thing that I learned is that only 5% of the people, on average, dream of making a discovery. A cool dream that I liked very much, and I think it was on top of the list of the most frequent dreams that are nice, I think, because maybe falling is not such a nice dream. But a very cool dream is to fly. And so dreams sometimes look a little bit like this picture. But when I think about flying, well, several of us came here by flying. And so is it flying something real? Is it a dream? Or is it just magic? So I went back and found David Copperfield, who, in complete simplicity, was flying in the air. And when I saw the video, I thought there was something on the bottom. But he's going up and swimming in an absolutely natural manner. And then at some point, he will even turn around. And this is something that caught my attention. So here, to me, it was a little bit difficult to find the boundary between a dream, magic, and reality. So from the dream, I switched the question to what is magic. And something I found is that it is the power of apparently influencing events by using mysterious or supernatural forces. And of course, we know that this is kind of a contradiction, because this is like making the impossible happen. But if something happens, it's not impossible anymore. So where is the boundary? And often the boundary is in technological advancements. Because if we are not used to something, and we make something that is not uncommon because of a specific technology, then that is magic, and that can be also a dream. And indeed, I was not the first one to think this. There is somebody that is much more well-known than mine, Arthur C. Cope. He is one of the writers of 2001 and Odyssey in Space, who said that any sufficiently advanced technology is indistinguishable from magic, and thus from a dream. So this means that if we go back in time, we should find some magic that are very, very simple. And indeed, if we go back 2,000 years, this is the Temple of Hieron in Alexandria, and these are the first, probably, sliding doors of history. So what was happening here is that fire was heating up some water, creating a pressure, and pressure was making the water go to this container. This container was coming down, pulling the ropes, and the doors were opening. And of course, the bottom part cannot be seen. And therefore, 2,000 years ago, this looked like something absolutely amazing. But I'm sure that most of us, maybe all of us, went through some sliding doors today. For sure, those who are in the hotel. And we didn't even care. But we had some magic very close to us. So indeed, if we make one step 2,000 years ahead, then the boundary that we have to overcome to see something magical happening is much, much higher than sliding doors. And so if I go back to David Copperfield, well, now we have to make the Statue of Liberty disappear. And this takes a while, but he takes a curtain, he puts the curtain on, then magic happens, slowly, by touching a radar. And as you will see, with the power of apparently influencing events, he will turn around at some point, look at the curtain, and just after he turns around, the curtain drops down, and the Statue of Liberty has disappeared. So, well, we went through some sliding doors this morning, but this, I guess, that is much more surprising for many of us. And this is a footage from a helicopter, so it's not so easy of putting a black curtain in front of the audience. There was a live audience there. So that's absolutely, to me, is stunning, even though by digging a little bit, we can kind of understand how this was done, what was the technology that was used. So back to Arthur C. Clarke, I hope that now I convinced you that any sufficiently advanced technology is indistinguishable from magic. But if we add 4 more letters, we can state that any sufficiently advanced nanotechnology is indistinguishable from magic. And to take this even a little bit farther, we can say that any sufficiently advanced chemistry is indistinguishable from magic. So now, if we want to make a chemical dream, then we need to understand what is the barrier that we want to overcome. What is the limit that seems impossible to overcome, but somehow we might be able to do it. So what is this limit that with my dream I want to apparently overcome? Well, it's the dream chemistry, so I had to aim high, so I said, okay, let's go bold, let's go for the second law of thermodynamics. And of course, in chemical terms, this means that for a given reaction, the Gibbs free energy of this reaction, for this reaction to happen, needs to be lower than zero, needs to be negative. There's no way to escape this, apparently. So this is something that implies that an opposite reaction, there is a reaction with a positive Gibbs free energy, something that goes to a product that has a higher free energy than the starting material, is thermodynamically impossible. And actually, this is something that has fascinated not only chemists, but also physicists, for example. And here there is a very famous one who described this thought experiment. And here what is happening is that you have to imagine this system at the nanoscale, down where Brownian motion is dominating. And he imagined a system in where atoms or particles were bouncing on a pole, and a ratchet was moving directionally. And actually, he has shown that this is impossible, because down at the nanoscale, the thermal energy essentially cannot distinguish on the shape of the barriers, and therefore rotating in one direction or the other direction is equally possible, is equally plausible. But some people were actually forced to think about these problems, because in 2016 there was the Nobel Prize for molecular machines, and of course there, molecular motion and directional motion are the core of the issue. So it's not surprising that among the few strategies that humankind has to perform endergonic reactions, we find the light-driven molecular rotor of Penferinga. And I've put this motor just to imply many light-driven systems. So using light is one way to overcome endergonic barriers, and we have seen it also this morning in a very nice presentation. A different strategy that is also very general is the possibility to alternate conditions. And here we have another Nobel Prize winner, just as an example of a category that is actually very, very broad. And what we are seeing here is a molecular axial and a macrocycle, and the two assemble only because we have a continuous alternation of conditions. But sure, if we use a little bit of an holistic approach, then we don't have to focus only on molecular machines. When we have activating agents, for example, dicyclohexyl carbodiamide that forms dicyclohexylurea, then we can form an ester bond, and under certain condition, this reaction is endergonic, is not thermodynamically favored. Or, to conclude, oscillating systems, these are also systems where locally we have something that is endergonic that is happening. So, yeah, if we look at the past, there are already some cases in which this boundary has been overcome. So we are in that gray area. But to me, what is fascinating is to look at nature. So in nature, endergonic reactions are absolutely ubiquitous, and they are not performed in any of the ways that I've shown you before. So for this example, they are at the basis of conformation changes in kinesin. I can speak because inside my body there are endergonic reactions happening. They are at the basis of adaptation, like the structure of cell is something that is endergonic. In all our cells we have microtubules. And then we just saw the importance of ATP synthase in the introduction of the last talk. And what happens in ATP synthase is that we have a proton gradient that has some energy and transfer its energy to the synthesis of ATP. And in all these processes, these endergonic reactions are enabled by coupled catalytic processes. There is a way that is significantly different, fundamentally different from the ways that I've shown you before. And of course, we are not alone in the world. For in particular, young people like me and the speakers, we build on the shoulders of giants. So if we look in the literature, where there are at least 2 or 3 examples of reactions that exploit these principles. And in particular here, you're seeing a couple of works from the group of Lee. These are absolutely amazing works. And I should say that to me, this is not the state of the art. This is far beyond the state of the art. And what is happening here is that by continuous protection and the protection here of this secondary alcohol with a FMOC group, and here of this primary amine with this FMOC group. So this protection and the protection reactions are coupled with a directional movement. In one case of this yellow microcycle around the white microcycle, and on this case they are coupled to the assembly of these microcycles along a thread. But in all these cases we are speaking about interlock structures associated with directional motion. And of course, if you let me go back to the analogy with flying, well, if we see, imagine to be like maybe 200 years ago, and you see a hot air balloon flying in the air, okay, so this is an object that is flying, but up there is room for Boeing 747 that goes from one continent to the other. And here I think we are in a similar situation, so this is far beyond the state of the art. These are impressive molecules, but you can imagine how difficult it is to make these molecules. Actually, how low is the efficiency? This is something that we have to recognize. And also the scope. So here we have directional motion. And these systems operate in organic solvents. And there's much more on the bottom, to quote somebody that I've shown you on the screen before. So my dream is to realize endergonic reactions enabled by chemical catalysis. And in particular, I think that it is possible to realize conformation changes, adaptation, and transductions in fully artificial systems by implementing a theory-guided approach. So, having said what a dream is, to make impossible reaction happen, then we have to go to the basics. And I will go back to the motor of Feringa. This is light-driven, so the principles will be different, but this is a step towards understanding the reaction mechanisms. So this is a motor that has 4 steps. It is light-driven. And let's look at it a little bit more in detail. So what happens here is that these are the 4 steps that we have in the motor, and 2 are photochemically driven and 2 are thermally driven. So in the analogy, if we want to move from light-driven system to chemically driven system, we have essentially to get rid of the light-driven steps and substitute them with chemically driven steps. And this is something that was proposed only at the theoretical level by Diana Stumian and Fraser Stoddard in a very nice review. And because we discuss rotation, we can take a biaryl that rotates around this atropoisomeric axis. There I have schematized like this with a yellow rod and a white rod. So what happens is that we need to find again the 4 states, and the first step will be binding of a substrate to this machine. There is catalysis involved, so we need to have a substrate. And then when the substrate is bound to the machine, we will have half rotation. And this half rotation will happen, for example, via this transition state. This means that the big white dot will go over the big yellow dot, affording this state, which is still a bound state. So we have the catalyst and the substrate that are bound together. And then only in this state we will have the release of the product. So we get back to this state, is still not the initial one, so we have to close the cycle. And what is important for directional motion is that this rotation will happen in the same direction of this rotation. And for this to happen, we need to switch the barriers. So here, the white circle was going over the yellow circle, and here the white circle will go over the small yellow circle. And this will complete the cycle. So what is happening in this reaction sequence is that we have a catalyst that is operating, and its operation is coupled with its rotation. But there are a few things that we can learn from this scheme, because of course that's a very simplistic way. We just show the path that is productive, the one that affords rotation. So if we consider this system, well, what can happen is that the substrate can also bind to this other state, and the product can also release in this other state. So we have multiple catalytic pathways, and this means we have a first hint that motion emerges when one specific catalytic path prevails over the other. So we need to find tricks to let one catalytic path prevail over the others. And we can also learn something more from this basic scheme. And this is that, in fact, what we are looking at is a catalyst that has two different conformations, because we can focus only on one of the two sides, only on one conformation, and we have substrate binding and product release, so that's like a regular enzyme. And we can also forget about that part, look at the other, and again we have substrate binding and product release. So here we learn that we are looking at a catalyst with two conformations. So this means that bistable catalysts can undergo endergonic reaction. That's a first key piece of information. But if we want to make endergonic reaction happen, we would like to make something broader than just motion. So then we can ask ourselves, how can catalysis drive self-assembly? So here we don't just have a molecular conformation change. Here we have really the assembly of different molecules. And I will discuss this specific case. There is the minimal model for microtubule assembly. It is absolutely simplistic if you are familiar with microtubule assembly, but I decided to put microtubules there to give you a flavor of how this can be related with microtubules that then have much higher complexity. So the target will be to obtain this high energy state. So what we have here is GDP tubulin dimer that can self-assemble into microtubules, but this reaction is not thermodynamically favored. So the microtubule will not form spontaneously. So what happens again is that a substrate, in this case GTP, will replace GDP in the tubulin dimer, forming a different dimer that is now prone to self-assembly. And this will create a low energy, stable, thermodynamically stable, GTP-rich microtubule. But then, in the GTP-rich microtubule, we will have catalysis and release of the phosphate, in full analogy with the cycle that I've shown you before. So what we have here, it is a cycle, and to understand which of these states will prevail, we need to know what is the slow step. So if the slow step is the microtubule disassembly, then what we have is a reaction cycle with accumulation before the slowest step, and therefore we can expect that in the presence of GTP, we will accumulate the GDP microtubule. So if we consider this reaction sequence, shown with the green arrows, the net reaction is the hydrolysis of GTP to give to release the inorganic phosphate that is coupled now with an assembly reaction. So this means that tubulin dimers, they catalyze GTP hydrolysis, but to catalyze the GTP hydrolysis, they need to assemble. And again, also in this scheme, as before, we can find the opposite path. That is, binding of GTP to the GDP-rich microtubule, then disassembly, and then catalysis. So now what we will do is we will compare the green and the gray reaction path. When we look at these two paths, in both cases, the substrate is converted into a product, here and also in the upper path. But in one case, this reaction is coupled with an assembly reaction. In the other case, this reaction is coupled with a disassembly reaction. So if the conversion of substrate into product, it is sufficiently energetically favored, then what we have is that both paths are thermodynamically allowed, and it is kinetics which rules which one of the two will prevail, and therefore whether assembly or disassembly will prevail. So I really want to convince you of this concept, because it's very key to realize in principle any endergonic reactions, and therefore I will show you some simulations that have been done for dimer self-assembly. So we are looking at exactly the same reaction network that I've shown you before, just a little bit smaller. And what we do here is that we enclose everything in a box. We provide the substrate continuously. We remove the product continuously. and therefore we will reach a steady state, and we look at the steady state concentration of these states. So the larger the circle, the more populated a certain state is, and starting from a system that is kinetically symmetric, there is no kinetic preference for the assembly or disassembly, this is the state that is mostly populated. And we ask ourselves the question whether this state is an equilibrium state or not for the self-assembly reaction that we want to shift. So either this one or also that one. So is it an equilibrium condition or not? To address this question, we can remove all the interaction with fuel and waste, and we let the system relax to equilibrium. And as you can see here, strikingly, the population are exactly the same. So this means that when kinetically assembly and disassembly are equally favored, then we cannot affect self-assembly equilibrium. So substrate consumption does not affect self-assembly equilibrium in systems that are kinetically symmetric. So to prove that this is really the key, we go and do the same thing for a system that now is kinetically asymmetric. So the thermodynamics of the system is absolutely identical to the system that I've shown you before, but in this case, the green path is faster in comparison to the gray path. And again, we provide the substrate, we remove the waste product, and we see that the concentration of the high energy state is now much larger. And again, we want to confirm that this is a non-equilibrium state, and therefore we remove all the interaction with fuel and waste and let the system relax to equilibrium. And as you can see, we have a dramatic shift in population, which confirms that when we have kinetically asymmetric system, we can achieve endergonic reactions and population that are not compatible with equilibrium. So this brings us to the second design principle, that is that we need to embed kinetic asymmetry in bistable catalysts to enable endergonic reactions. So I hope that to some extent the basics of realizing an endergonic reaction can be clear, at least to some extent. So we need something that is bistable, and we need to install a kinetic asymmetry in the system. But then, how can we make the reality? How can we make the dream reality? Well, first we need a slow equilibrium to toggle, so we need bistable catalysts. And I propose to use these atropoisomeric molecules. So these are molecules that can rotate slowly around this axle, and this axle. And therefore, in this way, they exchange between two states. But the concept is quite general because, for example, we can even think, instead of a conformation change, we can think of a Diels-Alder reaction. Here, the yellow part and the white part are two partners that can react. They are in equilibrium with one another, the separated state and the assembled state. And here, to use a cartoon to represent some of these molecules, well, I will show this image here. We have the two parts. We have one that can rotate. But the peculiarity of this system is that actually, in all these atropoisomeric molecules, I have inserted a second origin of asymmetry. Here we have point chirality. Here we have the cis-trans isomerization of amides, and here we have a second bond that is atropoisomeric and it is blocked. And the reason why this is critical is that if we have something that has only an atropoisomeric axis and it rotates, the relationship between the two states upon rotation will be enantiomeric. So there will be mirror image from one another, and therefore they will have the same properties with respect to something that is achiral. But in this case, because there is a second element of chirality that does not isomerize, the relationship between these two states is diastereomeric, so the properties will be different. So we can expect different properties, and of course it will be different catalytic properties in one conformation or the other. And indeed here in the following discussion I will discuss an anti-conformer where the two catalytic units are far apart. The pink part will be the catalytic units, and the syn conformer in which the two catalytic units, the two purple parts, are close together. So now we have to discuss the second element that is required, that are these catalytic units. So we need catalytic units that are impacted by conformation changes. This will give us the asymmetry in catalytic properties. And there are a few options available. So for example, Recently, amines became very popular as organocatalysts, in this year especially. And for example, we can imagine to catalyze a Diels-Alder reaction. And this reaction proceeds via an iminium intermediate that can be stabilized by hydrogen bond donors. So if we think of putting the two units with a secondary amine and the nitrogen bond donors, then having the hydrogen bond donors close or far from the secondary amine will impact the reactivity. Another possibility is to use a very simple carboxylic acid. We are not used to think of it as a catalyst, but it can serve as a catalyst for the hydration of carbodiamides. In this case, again, the unit that can cooperate, again, is nitrogen bond donor, because it is known that the proximity of hydrogen bond donor speeds up at least 6 times the rate of carbodiamides hydrolysis. So again, this is another catalytic pair that can be affected by conformation changes. And then we can also use more classical motifs. So for example, these are triasa cyclonone macrocycles that, when methylated, are very well established catalysts for the hydrolysis of a number of esters, including phosphate esters. And they are known to be cooperative catalysts. So when there is only the monomer, the catalytic activity is very low. When we have two units that are close together, the catalytic activity is much higher. So now we have all the ingredients to realize conformation changes, adaptation, and transduction in artificial system. So starting from a molecule that can slowly rotate, what is expected is that the substrate will bind, for example, to the anticonformer. Then we will have the conformation change, because here catalysis will be slow, but upon conformation change, the rate of catalysis will be much higher. Catalysis will proceed in a fast way, releasing the syn high energy conformer. And because this reaction is relatively slow, then what will be observed is the accumulation of this high energy state. So this is how we can realize target endergonic reactions. And of course, if we look at the sequence of orange reactions, again, what we have is that we have used the energy of a substrate and its conversion to a product that has been coupled to a conformation change from anti to syn in this general cartoon of a catalyst. Of course, in the same scheme, there are also the competitive reaction paths that I've shown you before. So the substrate could bind to the syn conformation. Then we could have rotation and release of the product in the anti-conformation. And if we compare the two catalytic processes, the two competing processes, then again what happens is that we have the conversion of a substrate into product. In this case, it is coupled with the syn to anti-conformation, which is the opposite reaction. But the reason why now the first reaction, the orange reaction, is kinetically favored over the second reaction is that if we look at the product release step, this product release step is slow in the anticonformer because the two catalytic units are far apart, and this product release is fast in the syn conformer because the two catalytic units are close together. So you can imagine that we can use very solid reaction to prove this strategy, but then we can move to more interesting reactions. And I picked one as an example, and it's the hydrolysis of ATP. So if we embed in the same catalyst two cooperative units that can catalyze the hydrolysis of ATP, what will happen is that again we expect ATP to bind, isomerization to rotation to occurs, and then faster catalysis will lead to a high energy syn conformation. And the reason why I find this particularly fascinating is that what is happening here is that we are using ATP, the fuel that we also use to power artificial molecular machines. And so down this road we can imagine to have molecular machines that exploit the principle of that are used in nature and that operate in our body in synchrony. So overall this is an endergonic process powered by ATP hydrolysis. But of course the strategy is very general, so we can think also of different reactions. And before I have shown you Diels-Alder reactions that bring two molecules together, and we can use this to realize adaptation in chemical systems. So for example here what you're seeing are two partners of Diels-Alder reactions, And this means that under experimental concentration, we can have the system more shifted towards the separated components. This is just a matter of concentration. But what can happen here, in full analogy with what we have seen before, is that the substrate can bind to the substrate anchor. And we expect catalysis again to be slow in the disassembled state because we have the two catalytic units that are far together in space. But then when the Elsalder occurs, then the reaction speeds up incredibly because the two catalytic units are close together. And therefore, we can have product release and formation of this high energy state that would not form under thermodynamic conditions. So in this case, what is happening here is that we are driving a dynamic covalent reaction. So we are assembling matter, exploiting energy from a different source. And we can think of studying dynamic libraries to show adaptation. There is the change of population depending on a certain stimulus, not according to Le Chatelier principle, essentially. There are different definitions. This is one that I'm mostly comfortable with, but there are several definitions available. So in this case, what we have is that, again, we have a dynamic covalent library. We have only one, you can imagine as a die-in, and this as a dienophile. So we have two dienophiles, but one is catalytically active, whereas the other is not. So you can imagine that under equilibrium conditions, if the structure of these molecules is similar, one can expect similar population of these two states. So at this stage, we are under thermodynamic control. Thermodynamics governs the population of the different states. But then we can add a substrate that will convert into a product. And by doing this, it will promote the formation of the adduct that is catalytically competent. And because only one of the two adducts is catalytically competent, then we will have accumulation of a specific adduct. And what is happening here is that we have an endergonic control happening. So we are not anymore in thermodynamic control. It's not the thermodynamic stability of matter that controls the outcome. We are not under kinetic control. It's not the fastest reaction that dictates which is the molecule that accumulates. We have a new form of control that is endergonic control. The molecule that accumulates is the one that is better suited to absorb energy from the environment. And if you want, we can put this also in an evolutionary perspective. So some scientists think that we are better suited to absorb energy from the environment. And then, as a final part of my dream, I imagine to realize a transduction in artificial chemical systems. And I will recall what transduction is in this context, and now I'm using this word, by using ATP synthase as an example. So we have seen that ATP synthase exploits a proton motive force, a difference in concentration of protons, to promote the synthesis of ATP under conditions in which ATP would not form thermodynamically. And this is mediated by the mechanical action of ATP synthase that in this process rotates. And of course, the system is very complicated. It is included in a membrane. We can look at the complexity of the system, but we can also turn it the other way around and look at the simplest system that can imitate ATP synthase. And this is what I'm proposing at the moment. So what I do think that is possible to realize, even though it's very challenging, is a dream, is to use the same bistable catalyst that I've shown you before to realize energy transduction. And the initial part will be the same. So imagine that these molecules operate, for example, according to aminocatalysis that proceeds via iminium ion, and this gives a difference in catalytic properties. Then what will happen is that if we start from an equilibrated mixture of the two conformations, and we feed this mixture with the reactants of a Diels-Alder reaction, then the Diels-Alder reaction, catalyzed by our machine, will form the product, but also will form the syn conformation of the catalyst. And so far, this is exactly what we have seen before, so I'm sparing you the whole reaction cycle. But what is also true, according to the very same reaction scheme, is that actually also the reverse reactions are possible in principle. So this is exactly like two compartments that communicate with one another. So if we have one compartment that is in equilibrium and we add the disequilibrating components of the other compartment, then we drive one reaction away from equilibrium. And in the forward reaction, what is happening is that the components of the Diels-Alder reaction are driving the formation of a syn conformation. But we can also look at this very same equilibrium in the opposite way around. So this means that if we start from an equilibrated mixture and we provide only the substrate of only the product of the Diels-Alder reaction, equilibration of the Diels-Alder reaction will also drive in the opposite direction the formation of the anti-conformer. And again, what is also true in the very same kinetic skin is that if instead of starting with the equilibrated mixture of the catalyst, we start with the equilibrated mixture of the substrate and product, and we feed only a specific conformation of the catalyst, then the opposite coupling is also possible. So the relaxation of this catalyst will be coupled with the formation of this high energy product. And the reason why this inverse coupling with the molecules that I've shown here is essentially impossible is that this Diels-Alder reaction is completely shifted towards the product. So it will be impossible to measure this reaction. So to measure this process, we need a Diels-Alder reaction that is slowly reversible, where we can measure both one kind of both the reactant and the products. And therefore, what we can use is Diels-Alder partners that are much more activated, and therefore the reversibility is much higher. So this means that the inverse coupling, that is the addition of a syn conformation, can drive the disassembly of a Diels-Alder component, that is, makes it possible to release high energy molecules at concentration that are not compatible with equilibrium. So in the overall cycle, what can happen is that if we start with an equilibrated mixture of the two conformations, and then we add this high energy substrate, this can convert to the product and form and accumulate one specific conformation of the catalyst. But then relaxation of this conformation of the catalyst will be coupled to the opposite reaction that will disequilibrate. So overall in this reaction network, what is happening is that the energy of a favored Diels-Alder reaction has been transferred to an unfavored Diels-Alder reaction in the opposite way. So overall, I discussed endergonic reactions enabled by chemical catalysis, and in particular to obtain conformation changes, adaptation, and transduction in artificial systems. And because chemistry is not limited by biological evolution, then we can think that by implementing these systems and further exploiting them, we can open a plethora of opportunities. And if you allow me to go back to the analogy of flying, well, to me, this is a little bit like flying in the chemical space, because now we are not anymore bound to stay at the bottom level, but by converting a substrate into a product, then we can fly high in the chemical space. So I want to thank you a number of people, absolutely. So first of all, Joseph Moran, who has nominated me for this prize. And my past mentors, Alberto Credi, Leonard Prince, Maurizio Prato, Peter Sadler, Nathan McClenaghan, and Taguzo Aya. And it's particularly important for me to thank also all the group members, because of course, like the PI, they shape the culture of the group. We learn a lot from them, but in our daily interactions, the people that belong to the group are very important. And having recently started my independent research career, I want to thank my team, Simone, Fabiana, and Shanna, and all the staff at ISIS, the Institute of Supermolecular Science and Engineer, because I really appreciate interacting with them, and they're very helpful to grow as a scientist. Thank you very much for your attention. I'm happy to take any question.
Thank you very much, Giulio, for your talk. And again, we have time for discussion. So, Robert, go ahead. Wait for the mic, please.
I always listen to Barbara, so whenever she said don't talk without the mic, I don't.
Can't go wrong when you listen to Barbara.
There are two questions. I mean, when you're saying catalysis here, basically, for me, it's coupling two reactions and synchronize them in time. So whenever one of them has an upstream, upgoing with the Gibbs free energy, another one is downgoing. So overall, if you sum it up, the total change of the free energy will be negative.
Exactly, absolutely.
But you're mentioning catalysts. What for you is a catalyst in the case of the kinesin motor?
In the case of kinesin motor, so the hydrolysis of ATP is much slower in the absence of the kinesin motor.
So what is the catalyst and what is the substrate?
Oh, the catalyst is tubulin, the tubulin that the kinesin that hydrolyzes ATP, and the substrate is ATP, and the product is the inorganic phosphate and ADP.
Because, for me, it's just a molecular motor that uses the energy of the ATP to take the part of the molecule up and make slight conformational changes that changes the kinetics that you mentioned. And then I can count this as a heat that I put into the motor. And then there is the work of the kinesin motor. And then if you divide this work by heat, you will get roughly the Carnot cycle efficiency for the motor itself, despite the fact that it's powered by the thermal noise.
Well, so it's powered by the thermal noise, but it's powered by the hydrolysis of ATP in the sense that if we put an equilibrium concentration of ATP with the product of its hydrolysis, kinesin will not move directionally. So we need the energy of the hydrolysis of ATP to, on average, according to Brownian motion, move directionally. This is well established. Yeah.
But this is only due to synchronization of the two. So the time needed to take the protein up from the support, and then the time it takes for the leg to be put down. The one takes about 10 milliseconds, the second takes about 2 milliseconds.
I fully agree, and we can see this effect also here, if you want. So I think that at least in my community, synchronization is not frequently associated to this term, but I fully understand, I think, and I agree. And for example, here, the speed of this reaction here of the switching is critical for the machine to work, because if this reaction is slower, then this catalytic path that does not involve the conformation change then will dominate, and we will not see the reaction. So absolutely, if we say that this synchronization between that part...
was something that I could not understand. What is the catalyst for the motion of the kinesin? Because I see ATP that changes to ADP, so it changes its state, so it cannot be a catalyst. Then I see a protein that changes its position along the microtubule, and then the microtubule is just a surface support for all this motion. So
yeah, but
I don't see the catalyst.
So it is kinesin and can switch between two states in analogy what I've seen with what I've discussed. And the analogy of conformation change is, let's say, the feet of the kinesin. One can be back and one can be front. And it is this Brownian motion that is coupled with catalysis. So it is kinesin there is a very nice article from Dina Stumian in Nature Nanotechnology that describes exactly this mechanism. Exactly, yeah.
Okay, yeah. So let's move on directionally to the next question. Okay, well, I'll ask one. So, in the beginning of your talk at the magic department, you said your reactants are more stable than the products, and you do the magic by going from more stable reactants to more stable reactants to less stable products. And you said you're doing magic with the second law of thermodynamics. And I was thinking, is this the second law or is this the first law?
I would say it's the second, because entropy should increase in a closed isolated system better. In an isolated system, so in this case, for a chemical process, then we need to have an increase in entropy.
But what you showed, you said you're going uphill in energy. So to me, that's violating the first law of thermodynamics. It's a free energy. Let him answer.
But that's the reason. So we are discussing Gibbs free energy.
Both there? Both laws you're violating both?
No, actually, I'm violating none. So this is So okay.
When you set the scene for your talk, you said you're violating the second law.
I focused on the second one. Yeah.
Not the first one. All right.
I focus on the second one.
Uli.
Yeah, thank you very much. What I just wanted to ask is maybe a more specific clarification of the Diels-Alder reaction, because there you sketched basically only the catalyst and what this is. So what is this specifically that drives the Diels-Alder reaction? So as a chemical structure?
Yeah.
I don't see this here.
We can look at the structure here. So this is, in principle, is a classical Diels-Alder reaction that happens thermally. Actually, in this specific case, the binding constant, the equilibrium constant for this reaction is roughly 10 to the third. So.
Yeah, but the sketch of the biareal there, I mean, I really don't see a specific catalyst here.
In this case, we have to imagine that on this purple hands,
right,
we have two of these units here. So, for example, like a carboxylic acid and a nitrogen bond donor, like for example this acid here and this hydrogen bond donor, or each of these two. These are the arms of the molecules that I've shown. Yeah, and the same in the Diels-Alder reaction. So, on one part of the Diels-Alder reaction, we have one of these two elements. On the other hand, we have the other. On the other partner, we have the other one.
Okay, so you have basically a 2-point binding at each side, which brings the reactants basically close together after rotation.
Yes, actually, so what is really important is that the rate of catalysis and actually the Michaelis-Menten parameters in the two conformations are different. So then, in general, very general terms, like the thermodynamics of this step, this doesn't matter in terms of it impacts the efficiency, but does not impact the directionality. This is an established result. So we don't need a thermodynamic preference to go here, but it makes sense that to increase the efficiency, we have a thermodynamic reference for that state.
Yeah. Okay, thank you.
You're welcome.
All right, do we have more questions? If not, thank you very much again.
Thank you.
I'd like to thank all the speakers today, and I'd like to thank everybody for coming and listening. Also the online connected people. Just few remarks before we close this. Please come tomorrow again at 9 o'clock. We will have the award ceremony followed by 3 lectures. The winners of 2020. Oh, there's light. Photocatalyst. The winners of 2020 and 2018 competitions, which are both in Warsaw. And then the talk by Magdalena Helmer about publishing in Nature. So please come. So that's for the general public. For the committee, we will have also for general public, there's still a coffee break and a small bite for everybody, so please take advantage of that. For the committee, after the quick coffee break, we will go and do the conclave, so to speak, right? We will not leave the room until the white smoke goes out. Or whatever. It does happen here in this building that we have white smoke. Okay, well, okay. We'll do some virtual white smoke. For the 5 of you, so you indicated which labs you want to visit, so Barbara will help you to kind of orient around. Maybe you can also take them to the top of Květák and show them around a little bit to get a feeling for the institute. Yeah, and then the 5 of you, Barbara, the last year winners, Robert, and a few others. So we will go for dinner at 7 p.m. And to make it easier for you, you will have about 1 or 2 hours to relax at your hotel room. So I will pick you at the hotel lobby at 7 sharp there. And it's, again, walking distance, very close, everything. So did I forget something? Except to thank you for actually, keeping us all in shape. All right, but I'll do that tomorrow morning. So, all right, thank you very much again. Thanks to everybody.